8.1, Understanding Logarithms. So logarithms is something new. Um, it is simply the inverse of an exponential function. So our exponential function is y equals c to the x. Inverse means we switch x and y. So it's x equals c to the y. This is also called the logarithmic. And we can either write it in exponential form like this, where we go c to the y equals x, or we can write it in logarithmic form. And this is how we write it in log form. It's log of base c, the exponent goes here, equals y. Okay, so a couple notes. Notice this is our exponent, and our base is down here. This is our base. These are equivalent forms of the same function, okay, the logarithmic, which is defined as the inverse of an exponential function. A couple of things built into the definition you need to know. In a logarithmic function, the base is always positive, and the base cannot be 1. Okay, so just some definition to add on to your sheet there. I always think of it as, when I read this out, I say, well, c to the power of what gives me the value I'm looking for. That's how I remember it and how I'll be speaking about it in this video. So now we need to evaluate logarithms. We need to find out what this equals. So log 749, log base 749. What does that equal? Basically what I'm saying is 7 to the power of what equals 49. So I'm going to use that same strategy from chapter 7 where I write things as a common base. Well, 49 can be written as 7 squared. So x must equal 2. So in other words, log base 7 of 49 is equal to 2. So we've evaluated that expression. Log 6 equals 1. So 6 to the power of what equals 1? Well, 6 to the x, we need to write 1 as 6 to the power of something. 6 to the 0, x equals 0. So in other words, log 6, 1 is equal to 0. Okay. Sometimes you'll see logarithms that don't have anything right here. And that means they're the common base, or they're base 10. This, in fact, is the button on your calculator a lot of times. It says log without a base. It's assumed that it's the common base, or base 10. Okay, so this is basically asking, is 10 to the power of what equals 0.001? Well, I need to write both sides as the power of 10. This is 10 to the negative 1, 2, 3. X is equal to negative 3. So log, the common log of 0.001 is negative 3. I'm going to erase this last one just so I have room for the final question here. Kind of stuck it in the side here. Log base 2 of the square root of 8. So that square root of 8 should be very big there. So 2 to the power of what is equal to the square root of 8? Well, 2 to the power of x equals 8 to the 1/2. That's the same as square root. It's to the power of 1/2. I need to write 8 with a base of 2. 2 to the x equals 2 cubed, because 2 times 2 is 4, times another 2 is 8. And this is all raised to the power of 1/2. 2 to the x equals 2 to the 3/2. is 3/2. So in other words, log base 2 of the square root of 8 is equal to 3/2. Okay, so just nothing very new, just a new form of writing exponential functions. Okay, a couple more to try here. We need to determine an unknown expression in logarithmic form. So now we might be given the exponent, we might be given the base, and we have to figure out what those things are. Okay, so log base 5 of x equals -3. In other words, it's saying x, sorry, it's not saying x, it's saying 5 to the -3 equals x, because we have our base to our exponent. Okay, this is like 1 over 5 cubed equals x. 1/125th equals x. So that's my answer for A. B. So this says base x to the power of 2 equals 36. So x squared equals 36. X is equal to plus or minus the square root of 36. X is equal to plus or minus 6. Okay, x is the base. The base in an exponential function we call c. We said by definition in a logarithm, the c must be positive. So I can reject -6, because c must be positive, and my final answer is x is equal to 6. This next question here, 64 to the power of 2/3 is equal to x. Okay, so that is like 64, the cube root, all squared. Okay, because this on the bottom means that that's the root, and then this is raised to the power. So that's how I got the cube root of 64 all squared. Well, the cube root of 64, 4 times 4 is 16, times another 4 is 64. So the cube root of 64 is 4. If you didn't know that, you could use your calculator. So I have 4 squared equals x, and I have x equals 16. Okay. So what do these graphs look like is our next question. It says, since logarithms are the inverse of a function, what will their graph look like? So what we're going to do here is we're going to graph y equals 2 to the x and y equals 2, and y equals log base 2 of x. And remember that this is the same as 2 to the y equals x. So you can see that these are inverses. We switched the x and the y. These are equivalent forms, these two right here. Okay, they are inverses of one another. So basically what it's saying is we are graphing y equals 2 to the x and its inverse. But its inverse is the logarithm. Okay, so first of all, let's do y equals 2 to the x, and I'm going to graph that with red here. So a couple of test points. If I put in -2 for x, 2 to the power of -2 is 1/4. So my first point is at -2 and 1/4. Okay. My next point, let's try -1. Well, 2 to the -1 is 1/2. Okay, and pause as I go along so you can do your graph at the same time. And then 0. 2 to the power of 0 is simply 1. So 0 and 1. Then I have 1. 2 to the power of 1 is just 2. So that point was at 1 and 2. Next I have 2. Well, 2 squared is 4. We can start seeing some exponential growth already. 3. 2 to the power of 3 is 8. and we're up there. Okay, so we can tell that this graph comes very close, crosses at 1, and then grows exponentially. Okay. Now I'm graphing the inverse. The inverse simply means we're switching those x and y values. Okay, so I have 1/4 and -2. 1/4 and -2, somewhere there. I have 1/2 and -1, 1/2 and -1. I have 1 and 0, 2 and 1, oops, 4 and 2, so I'm just switching my x's and my y's, and finally 8 and 3. Okay, so you can see that this graph gets really close here. It crosses the x-axis, y equals 0, x equals 1, and then it starts growing. Okay. A couple things that you should see right away. Because this is an inverse, it's like we reflected this on the line of y equals x. We've reflected. That's what it means to be the inverse. We've taken a reflection of that. And I'll show you this in Desmos in a second too. You'll see it even nicer than our graph here. So looking at the green graph, let's look at the domain. Okay, so all of the x values, it looks like the x values are always greater than 0. So we need to write that. I want to get rid of what I just did. There we go. So all x such that x is greater than 0, x is a member of the reals. That makes sense because what we've done is we've taken a positive base, we've taken a base and we've raised it to a number. So if you take a positive base, no matter what number you raise it to, you're going to get a positive value. What I mean by that is if you take 5, it doesn't matter what number you put here, you're always going to have a positive value. That's why we always get positives. Okay, the range. So let's talk about y values here. It looks like I can have, if this graph went on continuously, I could have any value of y. So y such that y is a member of the reals. The x-intercept. So it crosses the x-axis right here, and that happens at 1. The y-intercept, there is none. And the asymptote, well, it kind of looks like there is a bit of a vertical asymptote. It looks like it comes really close to, but it doesn't quite touch this right here. This is a vertical line, and that vertical line is x equals 0. Okay. I'm going to press pause and show the same thing on Desmos. Okay, so here I have my red graph, which is y equals 2 to the x. And here I have the inverse, which is log base 2 of x. And if you'll notice, it's like we've reflected about that line. And we could change the base to be anything, and we'd see that same relationship. So I could put 3 to the x, and then log base 3x. Still, they're going to be inverses of one another. That's kind of what those graphs look like right there.